for the next part to this problem, this is Chapter 2, Problem 4b. We are given this set of conditions. We have 150 milliliters of 0.1 molar sodium hydroxide solution added to 200 milliliters of 0.1 molar formic acid solution. Water is added to give a final volume of 1 liter. What is the pH of the final solution? Okay, so what do we have here? We have 150 milliliters of sodium hydroxide solution. Okay, that's 0.1 molar. All right, and we've got 200 milliliters of 0.1 molar formic acid solution. Okay, and water is added to give a total of 1 liter for the total solution. Okay, so this is not a weak base or weak acid equilibrium problem. This is a weak acid strong base problem. So when you react a weak acid with a strong base, what happens? That strong base is going to pull off the proton that from the acid. We have a monoprotic acid here until we run out of base, right? So let's write that balanced equation for that situation. So remember, formic acid is this, and it's going to lose this hydrogen right here, and it's reacting with sodium hydroxide, and we got a one-way arrow here to give us water plus Na, and then A minus is HCOO minus. Okay, so what's happening here? Let's get a different color. So we're losing this hydrogen. Okay, this hydrogen is going to react with this hydroxide. So this hydroxide is going to pull off the hydrogen to form water. Okay, and then let's do a different color. This formate anion will pair up with that's left over will pair up with the sodium to give us the sodium formate. Okay. All right, so that's our balanced equation, and so we don't need an ice table here because this is not an equilibrium expression, but we can use what's called a BCA table. That stands for before, change, and after. So let's go ahead and use a BCA table to figure out what we have so that we can calculate that pH. Okay, so we've got, how are we going to put our numbers in here? Well, for the BCA table, we're going to use moles. Okay, we need moles, and we weren't given moles. We were given milliliters and molarity. Okay, and so we need to find out how many moles. So first of all, initially was added 0.1 molar, okay, or let's say moles per liter of formic acid. Okay, now how do we get moles out of that? Because that's molarity, moles per liter. We know that that 0.200 liters was put in because it was 200 milliliters of that formic acid solution, and that gives us 0.02 moles of formic acid. Okay, and for the sodium hydroxide solution, we also had 0.1 moles per liter of sodium hydroxide solution. Okay, and what was added was 0.150 liters because we had 150 milliliters of that. And that's going to give us 0.015 moles of sodium hydroxide. Okay, so now we can plug that into our table. So we've got, for our HA, we've got 0.02 moles, okay, and we've got 0.015 moles of sodium hydroxide. Okay, so what's going to happen when these two guys react together? We're going to get a tug of war, and the sodium hydroxide is going to pull off all of the hydrogens that it can in a 1-to-1 ratio. So we're going to lose all of our hydroxide is going to react. Why? Because we have less hydroxide than we do acid. So minus 0.015 moles of hydroxide, and that's going to leave us with 0. We have no hydroxide left other than the autoionization of water. So for our change here, we've got minus 0.015 moles, because remember it's reacting in a 1-to-1 mole ratio. So that means that for every mole of hydroxide, we're going to pull off a hydrogen here, because this is a strong base, and that strong base is going to be strong enough to stoichiometrically pull off a hydrogen off of every molecule of the formic acid that it can. So until all of our hydroxide is used up. So if we subtract 0.015 from 0.02, we get 0.0005 moles of the acid after we add the sodium hydroxide. Alright, and so we don't care about the water here because it's a liquid and it doesn't count in this equation. So we started with 0 of our sodium formate, and we end up with 0.015 because we are creating 1 mole of that for every mole that was used up of the hydroxide. And so our change is 0.015. But we don't really care about that, right? So let's write everything down here. Our HA is equal to 0.0005. And our A minus is equal to 0.015. And our pKa is equal to the negative log to the base 10 of the Ka, which we were given in the previous section. Okay, so part A, which is 1.78 times 10 to the minus 4th. That gives us a pKa of 3.75. So remember our Henderson-Hasselbalch equation. In fact, I'm going to go back up here with it. Okay, pH is equal to pKa plus the log to the base 10 of the base over the acid. So the A minus over HA concentration. Now, you can use you can take this and divide by the liters, okay? You can take that amount, but you don't really have to here, because if you divide both of these by liters, you're going to have the same ratio. The ratio is what matters. So you can actually just plug moles in for this. So we can say pH is equal to 3.75 plus the log of 0.015 over 0.005. And so our pH is equal to 4.23. So that's how we find the pH of the this solution at this point in our titration.